Welcome to the next video about electric potential energy. In our first video we saw that a charge in a homogeneous electric field can have a certain electric potential energy associated with it. And what determined the potential electric energy that thing had? Its position compared to the negative plate in that homogeneous field. The further away it was from that plate, the more potential energy it had. Why? The more the Coulomb force could displace it. In the same way that the higher up an object is, the more energy, the more work can be done by gravity in this case. So you had gravitational potential energy as well due to height. Now, last year you will have learned that if you make a displacement, you have work. Work is the negative change in potential energy. Now this might be weird, but traditionally a difference in potential energy is the potential energy it has at the end of the displacement minus the potential energy it had at the beginning. Traditionally though, when a force moves an object, it will move it from high potential energy to low potential energy. So if you take low potential energy minus high potential energy, yes, you're going to have to reverse it, explaining this minus here in order to make it work. A more elegant way of putting it, when a force causes a displacement, it will perform work, and that work equals the difference in potential energy at the start minus the potential energy it had at the end of the displacement in this case. Now there are two typical ones, and there's a slight error in the course, so please fix that one. It's potential gravitational energy compared to potential electrical energy in this case. What is the main difference? It is the potential to be moved by, in this case, gravity. So it depends on its height. And that height is compared to ground level in this case. How much potential, what is potential electrical energy in this case? Well, it is the potential to be moved, in this case, by the Coulomb force, and that depends on its position compared to the negative plate in a homogeneous field, of course. So that's the main thing you have to take into account. Now, this means a charge can have negative electrical potential too. Just like an object could have negative potential gravitational energy in that case. Now, how on earth, when you think about it, could an object have negative potential gravitational energy? Now, imagine this. If I say that the amount of potential energy depends on its position compared to ground level, right? What if I take a shovel and I dig a very deep pit and I put a ball at the bottom of that pit? Is there a potential to move that ball to ground level? Not by gravity. Gravity is never going to make that ball float up and take it to ground level, to the surface of the planet. I am actually going to have to put in energy of my own. In other words, it has negative potential energy. I'm going to have to expend energy to get it to the surface of the Earth. In a very similar manner, a charge can have negative potential energy as well, negative electrical potential energy. When is that the case? Well, when I have to spend energy to move it to the negative plate. And when is that the case? This occurs when the charge is negative. Why? The Coulomb force will never take a negative charge to the negative plate. Just like gravity is never going to take an object below ground level to ground level in this case. Now, to make this more obvious, let's consider this exercise for a second. You have 5 different situations, and the distance, so they're all homogeneous fields, right? The distance is always the same. The distance between the charged object, a proton in these 3 examples, but an electron in situations C and E, it's always 1/4 of the way, meaning 1/4 of the distance is in between the proton and this plate, and 3/4 will be left between the other plate and the proton in this case. In which situations will the potential energy be negative? Well, let's talk about that. In this case, we have to start by analyzing our electric field E, because that is the giveaway to determine which of these plates is positive and which of these plates is negative. In this case, it's reversed because the sense of E is different compared to the previous exercises. Your electrical field will always be going from positive plate to negative plate, right? Now, in this case, if these charges are positive, I can rely on my Coulomb force to bring those protons towards the negative plate. Why? In these situations, this is a positively charged object. My Coulomb force is going to be able to move it towards the negative plate, which is my reference point. This is 0 potential electrical energy. If it's a proton here, same thing. You got my Coulomb force, or you have the Coulomb force. It is going to be possible to move it towards the negative plate. Right? Those 2 vectors have the same sense. However, if I consider this situation C, this is a negatively charged object, and in the previous chapter we saw that if the charge is negative, the Coulomb force will have the opposite sense of the electrical field. Right? There is no way that I can move this thing closer to that negative plate relying on the Coulomb force. I am going to have to spend energy to get it there. And we have a very similar situation in this case. It's a negative charge, so your Coulomb force is going to be pulling it towards the positive plate in this case. There's no way I can rely on it to drag it, to displace it towards the negative plate in this case. So it has negative potential energy. So in which of these situations will the potential energy be negative? These are situations C and E. In this case, why? You will have to spend energy to move the charge closer to the negative plate, which is always your point of reference. This occurs when the charges being moved are negative themselves. Right? So This is the reasoning behind C and E. There's only one situation where we've not drawn the rest yet, and that's this one. It's a positive charge, meaning my Coulomb force is going to drag it this way. Same sense as the electric field, because the charge is positive, meaning I can rely on it to be placed, to be moved towards the negative plate. Now, what about the potential energy in this case? Arrange these situations from the least potential energy, and I've given you a hint. The least potential energy means it actually has the most negative value in this case, to the most potential energy, in this case, the most positive value of the thing. Now, the devil's in the detail as well, because there's one last thing you have to take in mind. Your distance is always compared to the negative plate. So in this situation, the distance would be x. If we take situation A, however, the distance would be 3 times as much as a situation like in situation B. Same thing here, distance is x. It's always the distance to the negative plate, which is x. Here, the distance is 3 times x. There is still one tiny little detail you have to take into account, and that is the magnitude of your electric field. In one situation, your electric field, this is situation C, is twice as much as the other situations. However, if we have to determine which one of these two, C or E, is the most negative, in this case, in situation C, your electric field is twice as strong, right? So your potential electric energy depends on the magnitude of your field vector E, the magnitude of the charge being displaced, and, in this case, the position compared to the negative plate. Meaning, in this case, C, you have a very short distance, but twice the electric field. In situation E, you have triple the distance, but just once the electric field. Which one of these wins out? In this case, E is the most negative situation because your distance is more than the larger magnitude of your electric field. So E is the most negative situation, most negative potential energy, followed by C. The next one in line, in this case, well, those will be the positive potential energies, meaning A, B, or D. Now in this case, B and D have the same distance and the same electric field, meaning they are essentially mirror images of each other. So the potential energy is equal in both cases. Only in situation A, the distance is tripled, so that one has the most potential energy in this situation. Okay? Now, work occurs when a charge is moved in the electric field. If the displacement has the same sense as your Coulomb force, work is positive. Work can also be negative. When? Well, when the displacement is opposite to the force that should cause it. This means it's not the force, in this case the Coulomb force, that performs work, but an outside source that performs it. You can't rely on the Coulomb force to bring it closer to the negative plate. Never going to happen, just like gravity is not going to make a ball float upwards. Okay?